Hi everyone, Dr. Gray here. Today we are going to be working on Universe Target 6, understands how and why light years describe distances in the universe, understands the relationship of solar systems to galaxies to the universe. And today we're going to focus on the first part of this, understands how and why light years describe distances in the universe. And as you can see, what we're going to be focusing on is converting light years to meters and then to miles. So to start with, what is a light year? Very often when students are asked this question, because it contains that word year, they automatically think that a light year is a time unit, but it's not a time unit. A light year is a distance unit, just like meters or feet or kilometers or miles. The definition for a light year is the distance that light travels in 1 year. Notice that distance in that equation. And so, well, how can that be? And so we have to think about light. Light is really unique. It travels very, very quickly, faster than anything that we can possibly imagine, to be honest. It travels at about 300,000 kilometers per second. And so if light travels at 300,000 kilometers per second through the vacuum of space in 1 year, traveling 365 days, 24 hours a day, the light is going to cover nearly 5.9 trillion miles. And we've already talked about trillions now, so we know just about how big, or we have an appreciation maybe for how big a trillion is. So that's an enormous distance. And so the values that we're going to be working with today are, for our unit conversions, is that 1 light year is equal to 5.9 trillion miles. And because this is a science class and I want everybody to get better in metric units, it also is equal, 1 light year is also equal to 9.5 trillion kilometers. Over here on the side, this is just the way, or one way that we can write that in scientific notation for putting that into our calculators to do our calculations today. So, why do we use light years? Why not just stick with kilometers or miles? Well, the problem comes down to when we get to numbers that are too large, we really don't know what to do with them. When you get to a number like trillion, your brain goes, yep, that's a big number, but it really can't go beyond that. And so in order for us to really be able to think about distances in space, we need to make the number itself smaller, and so we need to make the unit bigger. For example, a few years back, scientists discovered a Earth-like planet in another solar system. Its name is Gliese 581c, and Gliese 581c is 630 quadrillion, 241 trillion, 920 billion feet away. Yep, that's a faraway distance. I can't tell you how long it would take us to get there and traveling at our fastest speed unless I did some calculations. All I know is it's a really long distance. If we move that into miles, clearly miles is a much larger unit, notice that the number gets smaller. Now it's only 119 trillion miles away. Okay, so, well, that's smaller than 630 quadrillion, but it's still a number much too large for me to work with. If we convert that into light years, well, now we're into 20.3 light years away. 20 is a number I can rationalize. 20 is the number of fingers and toes that I have. And so what this tells us is that if we were to get into a spaceship this afternoon, crank it up or speed up to light speed, and travel at light speed, at 300,000 kilometers per second, every day, all day long, for the next 20.3 years, that's how long it would take us to get there. See, numbers have meaning, but only in a comparative sense. For instance, we know that the number 5,000 is larger than 100. And so, if we're comparing 5,000 feet to 100 feet, well, clearly, 5,000 feet is going to be a larger distance because we're comparing the same kind of unit. What I would like you to do is to pause this video and make predictions. Which is bigger, 100 feet or 5,000 inches? 5,000 feet or 1 mile? 1 million inches or 25 miles? Once you've made your predictions, turn your video back on and we'll talk about those. All right, welcome back. And so, hopefully, let's look at these. Which ones have you chosen? Well, between 100 feet and 5,000 inches, the larger distance is the 5,000 inches. Because 100 feet, well, we got to have the same units. 100 feet would be 1,200 inches. And so, clearly, 5,000 inches is a larger distance. In the next example, the larger distance there, even though 5,000 is a much larger value than 1 mile is a greater distance because 1 mile is 5,280 feet. And in our last example, 1 million, well, that's way bigger number than 25, right? I would love to have $1 million more than I would love to have $25. But if we're talking about distances, 25 miles is a much larger distance. The 1 million inches, this is not quite 16 miles. It's like 15.78 miles. And so in order for us to think about, or in order for us to compare values, we always have to have those units be the same. So let's do a couple of conversions to look at, well, just how far away is an object if its distance is given in light years. Let's start with the Andromeda Galaxy. The Andromeda Galaxy is the closest neighboring galaxy to the Milky Way, our own galaxy, and it is 2.5 million light years away. Well, how far is that in miles? Your T-chart rules are here. We've gone through these before, so I'm not going to belabor those. We're just going to put them to use, but they're here in case you've forgotten them. We start out with our T-chart. Our starting information is 2,500,000 light years. We want to convert these units into miles, so we're going to put miles up top. We're going to copy everything that comes after this number down into this quadrant, so that's our light years. So light years goes here. And right here is our conversion unit. 1 light year is equal to 5.9 times 10 to the 12th miles. So let's fill that in. 1 is in front of light year, so we put the 1 on the bottom in front of our light years unit. And 5.9 e to the 12th miles, 5.9 e to the 12th miles goes in front of miles. When we put that into our calculator and do our arithmetic, this comes out to 1.475 times 10 to the 19th, E19 miles. Because our light years divide out, and when we multiply 2.5 million times 5.9 times 10 to the 12th, this is the value we get, a whopping large number. So here's your opportunity to practice. The Milky Way galaxy is 100,000 light years in diameter. What is that diameter in miles? Given that 1 light year is 5.9 times 10 to the 12th miles. Pause your video for a moment, do this calculation, and let's see if you can get it right. All right, welcome back. So let's do our calculation. We start with our T-chart. 100,000 light years across. We want to change this into miles, so miles is going on top. Then we want to copy everything that comes after this number, so that's our light years, down here. And just as before, 1 light year is 5.9 e to the 12th miles. And so after we do our calculation, we end up with the diameter of the Milky Way galaxy is 5.9 times 10 to the 17th miles. So not as big as the distance to the Andromeda galaxy, but still a whopping large number. Now, if we want to use kilometers instead of light years, well, this calculation is going to be done a similar way. The Andromeda galaxy has a diameter of 260,000 light years. What is the diameter in kilometers? And so we draw our T-chart. We have 260,000 light years as our starting information. We copy light years down in the bottom quadrant. We want to change it into kilometers. And note, remember, this is a slightly different value. That 1 light year is 9.5 times 10 to the 12th kilometers. And so after we're finished with our calculation, this is equal to 2.47 times 10 to the 10th, times 10, times 10 to the 18th kilometers. Now, another way that we make use of this relationship is to look back in time. When we turn our telescopes into the night sky, all of those points of lights, whether they're coming from planets or stars or nebulae, that light that we see is not the light that's being produced by those objects right this minute. Because even though light travels at 300,000 kilometers per second, it still has a long way to travel to get here. And so we can figure out just how old that light is by knowing how far light travels in 1 year. So let's look at this example. The Horsehead Nebula is 8,850,000,000,000,000,000,000,000 miles away. Well, we want to know how long does it take for light from this nebula to reach Earth? And if we're talking about how long, this is a time unit. Months, days, years. Well, the way that we get at this is to remember that in 1 year, light travels 5.9 times 10 to the 12th miles, which is really our relationship between light years and distance, which is why we can make use of that, which is why light years is a distance unit. But if we're talking about the movement of light, not people, not cars, not objects, because only light can travel at the speed of light, we can use this to determine the age of the light that we see. And so let's do this. Here's our T-chart. We have 8.85 times 10 to the 15 miles. Got to put that into scientific notation if you're going to use any of my calculators. There's too many zeros there to punch them all in. We want to change into years. And so we copy miles down onto the bottom, and we know that in 1 year, light travels 5.9 times 10 to the 12th miles. Well, this equals 1,500 years. And so what that means is that the light that we see coming from the Horsehead Nebula tonight, when you go out and look in the sky, is actually the light that left that nebula 1,500 years ago. So sometime in the 500s, not in the 2000s. Now let's look at this one more time. In the previous example, we were looking at the Horsehead Nebula, which is a huge distance away, and so it takes a long time for the light to travel that great distance. But what about Jupiter? How old is the light coming from Jupiter? Well, Jupiter is 588 million kilometers from Earth. And so if we want to know how old is the light coming from Jupiter, we want to remember that in 1 year, light travels 9.5 times 10 to the 12th kilometers, because our unit here is kilometers. So we got to make sure that we match up those distance units when we're doing our conversions. We do our T-chart. We have 588 million kilometers. Well, we want to know how long, so we want to change that into years. We have to convert from kilometers, and in 1 year, light travels 9.5 times 10 to the 12th kilometers. So, after some calculator work, we find out that this is 6.2 times 10 to the negative 5th years. Well, that negative 5, as our exponent here, tells us that this is a number smaller than 1. Quite a bit smaller than 1, in fact. There are going to be 4 zeros in front of that 6, between the decimal and that 6. So now we're dealing with a situation where that number is too small for us to know how big it is, right? Is that 1 day? Is that 1 hour? I need that number changed into something that I can rationalize. So let's start by trying to change it into days. So we have 6.2 e to the negative 5 years. If we want to change it into days, we put days in the top of our t-chart, years into the bottom, and in 1 year, there are 365 days. Well, this equals 0.022 days. Okay, well, that's better, right? It's not too small, but it's still, how much of a day is that? Is that a couple hours, a couple minutes, a couple seconds? Let's change days into hours. So add our t-chart there. 1 day is equal to 24 hours. And this equals 0.542 hours. Okay, now we're getting somewhere. So it looks like it's going to be about a half an hour. But let's try and get as specific as we can. Let's change that into minutes. 1 hour is 60 minutes. And indeed, it equals 32.5 minutes. And so there we have it. The light that we see in the night sky coming from Jupiter is actually the light that left there a little over half an hour ago. And that's it for today. Thanks for watching. I'll see you in class.